Okay, guys, here is our second spectrum that you should have in front of you. Again, we're only working with 3 carbons. And then notice this time that we have a couple of bromines in our example there. And if you look at your spectrum, there's only one signal. Okay, and of course, if you're looking at the chemical shift 2, we talked again about those halogens being in that 2 to 5 region. Bromine is not very electronegative, so a little bit more upfield. If you were hydrogens that were closer to fluorine, you'd probably be closer down here around 4.5 parts per million. But one signal, okay? So starting with our degrees of unsaturation, just like we did before, we have 3 carbons. So a saturated alkane would have 2N plus 2, which would be 8 hydrogens. Subtract out how many have, which is 6 hydrogens. Bromines count, or halogens count as a hydrogen. So we have 2, so we need to add 2. And then, of course, everything's divided by 2. So remember, oxygen doesn't affect your hydrogen count. Halogens, you need to include them in the count. Okay? So our degrees of unsaturation is 0 degrees. So no double bonds, no triple bonds, no rings, all single bonds. Okay? Alrighty, now since there's just one signal, that tells us a lot of information. It means that all 6 of these hydrogens, they need to be the same. Now you can't put 6 hydrogens on one carbon, that's not possible. So it's nice to think about how are hydrogens grouped on carbons. We see a lot of CHs, the methine hydrogens. We see a lot of CH2s. Those are the methylene hydrogens. And then, of course, our CH3 methyl hydrogens. So labeling this signal, this is a singlet. That's telling you that your hydrogens can have 0 equivalent neighbors. Okay, so wherever your hydrogens are on an adjacent atom, there can't be any more hydrogens. And of course, this is a halogen region. So you've got to have hydrogens near halogens, which if you look at your formula, we are. Now, there are only 3 carbons, and since we can't have them in a ring, the only way to arrange them would be like this. There wouldn't be any branching, okay? Now, let's try something, right? Sometimes we try something, it may or may not work out the first time. So some people go, well, how about we do 3 sets of CH2? So we could do that. And then we're going to check it and see if it works. Okay, so right now that looks pretty good, but then we have to add in the bromines, right? So if I put a bromine here and here, and you count how many signals that you're going to have, it's not going to be 1. So again, labeling our signals. How many signals would we have, just ignoring the splitting for a moment? Oh, that's my dryer. I'm going to have to turn that off. Hold on, guys. Awkward. Anyways, we've got that CH2 in the middle, which is very different than the CH2 right here. Okay, and of course these are the same as these. They totally have the same environment. It's a CH2 attached to a bromine. It's a CH2 attached to a bromine, and they're both attached to the same thing. So in this example, right, we're not going to have just one signal. This would be 2 signals. So we can rule this structure out right away. Even if you were to look at the splitting patterns wouldn't match either. For example, these hydrogens right here have 2 equivalent neighbors right here. 2 plus 1 would give you 3, which would be a triplet. Okay, now if we check these hydrogens right here, those 2 hydrogens have 1, 2, 3, 4 equivalent neighbors. And again, those total of 4 hydrogens are all the same because remember there was symmetry there. So those 2 methylene hydrogens in the middle have 4 equivalent neighbors. 4 plus 1 is 5. So we would be seeing a quintet in that halogen region, right? So that would be in that halogen region. which we're not having. Okay, so, oh, well, not quite the halogen. That'll be a little bit more upfield. We should say this guy over here, excuse me, is in the halogen region because they are more downfield, closest to the bromines. These ones would be a little bit more upfield, so let's cross that out. You know, maybe in the, maybe 1.5, because they're not too far from the bromine, so maybe the approximate alkyl area, maybe 1.5-ish, we'll say. Again, we're just getting the approximate area. So right now this doesn't match, so can't do the CH2s. So how about if we make something symmetrical with CH3 groups, right? 2 CH3 groups. So if I have a CH3 group here, okay, and I want to say, okay, these hydrogens can't have any neighbors. So if I attach a carbon right here, I can't put any hydrogens on it. So what else do we have? We have our bromines. So let me put our bromines right there. So that will eliminate the possibility of these guys having any hydrogen neighbors. And then our very last carbon would be right here. Now we have something nice and symmetrical. These are 6 equivalent hydrogens. So we're just going to get one signal. And if you look at these hydrogens, we say they have 0 equivalent neighbors. So 0 plus 1 is 1. That would be a singlet. And that's what we're seeing right there. Okay, so again, these two are the exact same type of hydrogens. We just have one signal, not 2, like we did in the case right here. And now we have this one fully analyzed. Okay, so we're going to work on the next one because it's very similar to something that we just did. Alrighty, so a little bit bigger of a formula. We have C4H8O2. Now I want you to go ahead and practice your degrees of unsaturation. Okay, so we've got 4 carbons, so 2N plus 2 for a saturated 4-carbon alkane. That would be a total of 10 hydrogens minus the 8 that we have over 2. Again, we're getting 1 degree. What does that 1 degree mean again? It could be a ring, which is a possibility, or a double bond. Okay. Now, we're not usually going to do alkenes or alkynes in NMR, so the only double bond that we could really hypothesize about would be a carbonyl bond. And bingo, we've got the 2 oxygens again. Now remember in the other video where we did a carboxylic acid has a carbonyl. Okay. And then we also have an ester that has the 2 electronegative oxygens in them. But there is a difference. Remember, this hydrogen would be a singlet because it has 0 equivalent neighbors, and it would be around 11 to 12 ppms. Okay, there's nothing here. So we've got no carboxylic acid possible. So we can rule this out right away. That means we're working with the structure of an ester. Now, a lot of times people flip-flop their ester and they accidentally put this R group over here and this one over here because we're not paying attention to our chemical shifts. So a lot of students get the splitting pattern to match, but not the chemical shift. So that's why we've got to really memorize those numbers. So let's label some of that chemical shift region like we're supposed to do in our analysis. So right here is hydrogens near alkyl groups, right? Furthest away from electronegative stuff. This 2 region, 2, 2.1, 2.2 are hydrogens adjacent to the carbonyl. Remember, all signals are from the hydrogen spin flipping in the NMR. And the chemical shift is telling you, again, it's proportional to the energy needed to do that spin flip. But it's also telling you what your hydrogens are near. Okay, so hydrogens near alkyl groups, hydrogens adjacent to a carbonyl. And then again, in terms of our ester, this would be near the oxygen, the lone oxygen over here. So again, this area should be right around 2. Okay. And this area that's directly attached to that oxygen should be, again, the closest to the oxygen would be around what we're seeing there, around the 4-ish. And then anything that's further attached over here would be in that 1-ish area, furthest away from those oxygens. Okay. So now we just need to look at our splitting pattern. Let's start with who's next to the carbonyl. That would be right here, okay? If you look, this is a singlet, and it's very tall, okay? So, well, kind of tall. It looks a little bit smaller there, okay? So sometimes the computer will draw that up a little bit longer, so we can't always trust the height of these. But again, it's a singlet, so that means these hydrogens have 0 equivalent neighbors. Now that's really easy to do if you think, because they need to be next to a carbonyl, which is going to be like a barrier, okay? And then here would be these groups of hydrogens. Now looking over here, there are no hydrogens on here because we still have to attach our 2 other carbons. We're only working with a total of 4 carbons, okay? So looking right here, we have a triplet, which we've seen an upfield triplet before. So these hydrogens have 2 equivalent neighbors because 2 plus 1 is 3. That's why we're seeing that triplet here. And then, of course, near that electronegative oxygen, we've got a quartet. Okay? And these hydrogens here, giving that signal, would have 3 equivalent neighbors. Okay? So we've got all our splitting pattern analyzed. We have our chemical shifts. We were able to figure out this structure right here. Okay, based on we needed some hydrogens that had no neighbors. We can't put a hydrogen on there because that would give us an aldehyde, and there's no 9 to 10 chemical shift. So we need to add our other 2 carbons. There's only one way to add 2 more carbons, a CH2CH3 group. And then we can go back always, always, always and check our work. Does our splitting pattern match? And does our chemical shifts match? Okay. So these guys right here, those hydrogens have 2 neighbors. These guys would be our triplet. And since it is furthest away from our oxygen, this should be right around that 1-ish region. So let's check. Yay, we've got a triplet in that 1-ish region. Now these 2 hydrogens here have 3 equivalent neighbors. So they would be our quartet. And I know what you're thinking. You're like, where's the other oxygen? I should have put it right here. So let's add that in there. We need our 2 oxygens for our ester. And that quartet, because it's right next to that oxygen, should be shifted downfield. So there we do have our quartet right there. So our structure matches. And then, of course, our singlet that is right there around 2 parts per million. So we are doing just great. Okay. Now, the common error that I see people do, again, is just matching splitting patterns. So this is what I want you to watch out for. So always check your chemical shifts. Okay, that's super duper important because a lot of people come up with the exact same splitting pattern and they do something like this, which you're probably going to see on a future spectrum. So just a little FYI. Always check your chemical shifts. So if you look at this one, it almost looks like the one we have up here, but the carbon groups, your R groups, are flip-flopped. Now, if I was checking my work, these hydrogens have no neighbors. So these hydrogens would be a singlet, and that singlet, since it's next to oxygen, would be in that 4-ish region. Do we have a singlet in that 4-ish region? No, we don't. Okay, so that's not matching. And if we look at these 2 hydrogens, this would be a quartet because they have 3 equivalent hydrogen neighbors. And since they are adjacent to a carbonyl, that quartet should be right around that 2-ish parts per million region. So checking up here, no, we don't have a quartet right there. So this is definitely not matching. Okay, so if we had these things kind of flip-flopped up here, then you could probably have this structure. Okay, so always check your work. It's really, really important. So I'm going to stop there. I'll probably do a couple more in one more video, but I want you to go ahead and get started finishing these day 1 spectrums. So you've got number 4 here, and again, make sure to read the information that they're giving you at the bottom. If it's hard to read, what is it that they're actually telling you those signals are? And I will be talking to you guys soon. Okay, bye-bye.